So number 2.
Good. Which form of electromagnetic radiation has the longest wavelength? You can either memorize the electromagnetic spectrum based on wavelength, or you can reason it out. Remember, Planck's equation, right? Energy equals Planck's constant times frequency. That's the Greek letter nu. I told you we're going to have some Greek in this. Or we can have like that, speed of light divided by wavelength. So if you think the way I do, the highest energy, you know the highest energy on the chart is gamma rays. And you know the lowest energy is radio. So if you're looking for the longest wavelength means to me the lowest energy. Because if the wavelength over here gets bigger, then that gets smaller. That's just mathematical progression. So the longest wavelength will be the lowest energy, and the lowest energy is going to be radio waves. That's the way I reason it. If you don't want to memorize the spectrum, like what order they come in, which you can do, that's fine. So the longest wavelength is going to be, well, let's see. Yeah, radio waves. I was looking at it wrong for a second. Yeah, radio waves is the longest wavelength. About 3. Which of the following frequencies corresponds to light with the longest wavelength? For this one, you look at the ratio, the relationship between frequency and wavelength, and speed of light is equal to the wavelength times the frequency. And this is, remember, this is in meters, and this is in reciprocal seconds, or hertz. And this, the speed of light is in meters per second. Right? So the units match. Meters per second, meters reciprocal seconds. So, and they're inversely proportional. Right? Remember, I've said this from the beginning. If you have 2 variables, the product of those variables is equal to a constant. They have to be inversely proportional. If this is going to be constant, one of these goes up, the other has to go down. Okay, so to answer the question, the longest wavelength is going to be the smallest frequency. So the biggest wavelength means the smallest value here. So we want to find the smallest value in that selection. And what I do is look at the let me do it over here so it'll be recorded. Is look at the powers of 10. Right. So there's 13, there's 5, there's 20, there's 12, and there's 9. So the smallest of those values is which one? It's 10 to the 5th. You don't even have to look at the coefficients. Are you missing something?
Oh, no, I was looking to see if this exam has any of those one questions, like which one of these are correct, like the statement.
Oh, yeah.
Choose how many are correct, but
I don't think this one does.
it doesn't look like it.
Yeah. That's good. Okay, so we don't have to go any further than the powers of 10. Right? We know that 10 to the 5th is the smallest one of that bunch. Now, if I'm sneaky and I put 2 up there with the same power of 10, then you go to the coefficient as a tiebreaker. Okay? Not that I would do anything like that. Okay, we got 6 and 8 on the board at the same time. All right, 6. A line in the spectrum of atomic mercury has a wavelength of 254 nanometers. Okay, that's atomic mercury. When mercury emits a photon of light at this wavelength, the frequency of the light is. if it emits a photon of light, and we want to know the frequency, then we're back to this equation. All right, we know lambda, we know the value of the speed of light, so we can solve for the frequency. But they have to be in SI units. Remember that. All right, this has to be meters. So what is that in meters? Remember the trick? Look at the units of measure. What does nano mean? Nano means 10 to the minus ninth, or 1 billionth. So it's 254 times 10 to the minus ninth meters. We just took that nano and put its numerical value in there. And it doesn't have to be scientific notation to stick it in your calculator. Your calculator is perfectly fine with this version. Exponential notation instead of scientific. Okay, so that will go in here. So what's the speed of light? You remember? Okay, and that's equal to lambda times 254 times 10 to the minus ninth meters. And you just solve for your unknown. And because we use the right units, oh, wait a minute, that's frequency, sorry. There we go. We're looking for frequency. Yeah, I was paying attention to the units of measure. That wouldn't give us wavelength because the meters would cancel and leave us with reciprocal seconds, and that's not wavelength. That's frequency. So you just move this one over here and divide it into that one, and you got frequency. Okay? And that should be, in the interest of time, that should be C. 1.18 times 10 to the 15th. Okay? You can stop me anytime. Number 8. Green light can have a wavelength of 543 nanometers. I always pay attention to detail. It can have a wavelength of 543 nanometers. So that means green light can have other wavelengths too. Right. Green light is what we perceive as green, and our brain interprets as green. But if you have an instrument that will spread the light out and actually measure the wavelengths, you'll find that green has many different wavelengths possible in that range. Anyway, what's the energy of the photon of this light? Now we're going back to Planck's equation. But we don't have frequency, we have wavelength. So we use this one, C over wavelength. Now the reason this works is this equation. Right? Frequency then would be, if we solve for the frequency, it puts lambda over here in the denominator, just like this. That's why it works. But we still got the same problem. Right. We need meters. So we can put meters in here. We've got that, we know, here. Now we need Planck's constant. All right, so that should be in useful information. Look in the back of the thing, you'll find several possibilities. There's one there, one page with a bunch of formulas and constants in it. You just have to study it and know where to find all this stuff. 6.626, H equals 6.626. 6.626 times 10 to the 35th minus 34. Minus 34 joule seconds. And then you put in the speed of light, right here, right there, and then you put in wavelength. Here, this one. This one goes right here. So that one times this one divided by that one will give you this one in joules. And if we do our math right, it should be C, 3.66 times 10 to the minus 19th joule. So a photon of light doesn't carry a lot of energy in it. It's very, very low. Okay, let's see who's next. We can get 11 in here fairly easy. Can I erase? Okay. $11, I think I said. How many of the following statements are correct? All right, let's look at them. So this is kind of like the one you and I are averse to, but not exactly. How many of these statements are correct? The importance of the equation E equals mc squared is that energy has mass. That's probably true. Yeah, I mean the equation says so. Energy equals mass times speed of light squared. Okay, thanks to Einstein. So that one's true. It's true. How about that one? Electromagnetic radiation can be thought of as a stream of particles called photons. Yep. That one's true. How about 3? Electromagnetic radiation exhibits wave properties. Yeah, that was the big brouhaha. Light is a wave. No, it's a particle. No, it's a wave. No, it's a particle. It's both. How about Roman numeral 4? Energy can only occur in discrete units called quanta. That question needs to be a little more complete. Energy with respect to electron transformations in the atom, their movements, occurs in discrete units called quanta. We quantize light into photons. So, as far as it goes, it's true. Okay? Now, the next one has several questions based upon this table. From the following list of observations, choose the one that most clearly supports the conclusion for the following questions. And I think there are 4 of them. So which one of these observations satisfies conditions for electrons have wave properties? What this is trying to do is to make the connection for you between the assumption of wave properties and what's the physical evidence for wave properties. All right. Emission spectrum of hydrogen. Does that support waves or particles? What kind of spectrum is it? It's a line spectrum, right? It has discrete. In fact, the visible range only has 4 lines in it. The only explanation for that is not wave properties. Okay? If it were wave properties responsible for that spectrum, then you would have a continuous spectrum. So A is not true. How about B, the photoelectric effect? That's a manifestation of particle properties of light. Right? Because one photon, one particle of light, strikes the surface of the metal, and if it's got enough energy, it'll eject an electron. It needs enough energy for the photon. Doesn't matter how many of them you throw at it. If it were waves, you could make the beam more intense, and then it would finally eject electrons. But the photon, the particle nature of light, explains the photoelectric effect. So it's not B. How about C? Scattering of alpha particles by metal foil. Oh, we're talking about electrons. I'm sorry. Yeah, it works both ways, light and electrons. Scattering of alpha particles by metal foil. That doesn't have anything to do with electrons. That has to do with the nucleus, right? That was Rutherford's gold foil experiment that used that one, right? So C is thrown in there just to twist your brain around. How about D? Diffraction. Remember what diffraction is? We have a barrier with a slit, and we got something coming at it. If light were particles, they'd be traveling in straight lines. These guys would get blocked, and this one would go straight through. And our detector would show a bright spot right there, and everything else would be dark. That would be the particle nature of light. But when we shine light on this slit, it doesn't do that. What it does is it behaves like a wave. Waves is traveling at the, let's just say we've collimated the waves so they're straight. They don't have to be. And when it strikes this, this serves as a point source. And makes a new wave. So it's dark right here, but it gets progressively lighter as you go out. Right? The only explanation for that, diffraction, is wave property. That happens with electrons and light. It happens with electrons, we know, because we built electron microscopes based on that principle. Well, that and electromagnetism. It's a combination. But diffraction explains wave properties of electrons. Because they will be diffracted just like light if we pass them through a slit. Okay, so 12 is, let's say D? Yeah, D. We found our answer, so we don't even have to look at the last one. Cathode rays, they're streams of photons. They're streams of electrons, particles. How about 13? Electromagnetic radiation has wave characteristics, right? For the same reason. Diffraction explains wave properties. Right? That's why it's the same answer. Electrons and atoms have quantized energy. What explains that? The best explanation is that emission spectrum of hydrogen. Why do you have only certain wavelengths emitted from a hydrogen atom? Let's see, we're on 13, 14. We're on 14 already. Because here's the nucleus, there's your energy levels. Right? 1, 2, 3, 4. When the electron jumps from here to here, it absorbs energy. Right? That's Planck's equation. I just put that in. That means energy. Or if the electron drops from an outer orbital down to a lower one, it emits energy. But we know that the quantization of the energy is true because there's nothing in between. These electrons can only be here, 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 or some other energy level. Without that quantization, you get a continuous spectrum because the electron can come from anywhere, any level, and you get white light from everything, and we'd be in big trouble. Well, science would be in big trouble because we couldn't learn anything about the universe. Now we can look at stars, we can look at some planets, take their spectra, and we can tell what's in their atmospheres based upon their spectra because it is unique in these energy transformations. If it were just white light, that wouldn't work. Okay, so 14 is A. And 15. Spacing between atoms in a crystal is on the same order as the de Broglie wavelength of accelerated electrons. You can use X-rays too. We haven't talked about de Broglie. What de Broglie said was that since the electrons and light photons have both particle and wave characteristics, we can treat them the same way. Only the equation now, instead of this, let's see, 15, instead of this one, instead of that one, for photons, now we can use the velocity of the particle, right, the velocity of the electron in this case, and it will have a wavelength and a frequency. Okay, that's the de Broglie wavelength, and it's also based on mass. So we throw in here, that's for light. A photon has a mass relative to its velocity. It's called the relativistic mass. But particles, like electrons, we can plug them in there also, only we have to use their actual velocity instead. And that will give us the energy, the mass equivalent of the energy for that electron based on its speed. Now the spacing between the electrons is, for the de Broglie wavelength, is the way we do, well, when I did it with soils, I used X-rays, X-ray crystallography. But electrons, we can do it with electrons too. They have very short wavelengths because they're high energy, and they have substantial mass, much more than a photon. But what happens is you've got a crystal structure of, say, atoms layered like this, and then you got another layer here. And what happens is the wave comes in and it's bent and reflected off these layers. So it comes out like that, and it comes out in, well, I don't want to complicate it too much. And what happens is there's an angle of reflection, right? And it's the same as the angle of incidence. I mean, the law of reflection applies to electrons as well as light waves. And the spacing between here allows you to develop an interference pattern. The best way to describe that is with a double slit. And if you have light coming in here like this, it hits these two slits. Now they're point sources for new waves, right? So if these lines are crests of your waves, when they meet, they reinforce one another, right? They make the light brighter. And when a crest meets a trough right here, they cancel one another out, and that makes dark. So instead of just a dark spot over here, or a light spot, on your detector, you get a series of lines based upon the constructive interference of those crests. And you can do the same thing firing electrons or X-rays at a crystal. It behaves similarly. So it comes in, you get a reflection off of here, like this, and you get a reflection off of here, like this. So you get constructive and destructive interference, and you can use that information to measure the distance between those crystals. It's really a very simple technique, but the math is a little complicated. We'll get to that next semester. All right, so that's just a taste of the future. All right, so the answer is D. Let's see, let's do these two together on the same screen. 16. The 4 lines observed in the visible emission spectrum of hydrogen tell us what? Well, let's see. There are no oddballs in there. They're pure statements for each one, so work our way down, and when we find the right answer, we can stop. The hydrogen molecules tell us that the hydrogen molecules they came from have the formula H4. I don't think so. This is an atomic phenomenon. Has nothing to do with the molecular structure. Now, some spectra of molecules, it does have to do with the molecular structure, but that is translated into the electronic structure as a consequence. So it's always based, those emission lines or absorption lines, they're always based upon electron movement into higher levels or lower levels. If it goes higher level, that means it absorbs. If the electron goes into a lower level, it means it emits. So it's not A. We could observe more lines if we had a stronger prism. Well, that's been tried. You take the line, the emission spectrum of hydrogen, show it through a prism like this. Light comes in and it splits out like that into its 4 lines. And then researchers, probably graduate students or even seniors, they put another prism here, right? And it goes out here and goes, doesn't split. They put another prism out here, it doesn't split. They could do it several times, it would never split. So there's not more than one line buried in that one. Now, some emission spectrums under certain conditions, they do split. And I used to use that phenomenon in atomic absorption spectrophotometry to assess the concentration of an element in the sample and remove interferences. So I won't say any more about that because I can see your eyes are glazing over. There are 4, so it's not B. There are 4 electrons in an excited hydrogen atom. I don't think so. If there were, what would you have? You'd have a plus, you'd have a 3- charge. Now, you can probably create those, but that has nothing to do with the emission spectrum. How about D then? Only certain energies are allowed for the electrons in a hydrogen atom. Bingo! That's the one. Quantized energy levels in the atom. (17) For which of the following transitions does the light emitted have the longest wavelength? Okay, we want the longest wavelength. Go back to the first one, I think number 2, when I was mentioning energy. Longer wavelength means lower energy. So the longest wavelength would be the lowest energy. So what transition gives you the lowest energy? It's the one where the electron moves the shortest distance, right, between energy levels. So let's say we're going from, 1 to 4. So if we draw our model of the atom, so we have 1 there, 2 is way out here, then 3 is a little closer, and then 4 is even closer than that. 1, 2, 3, 4. So what's our first choice? 4 to 3. So the electron goes from here to here. And we have 4 to 2. Right? And we have 4 to 1. And we have a 3 to 2. And we have a 2 to 1. Okay, which one's going to have the lowest energy, longest wavelength? That one right there, 4 to 3. It's the shortest jump. The lowest energy, in terms of energy, the lowest energy jump is from 4 to 3. That would be the longest wavelength. Let's see, 18. When a hydrogen electron makes a transition from n equals 3 to n equals 1, 3 to 1, and there's 2 stuck in there for good measure. It goes from 3 to 1. What's going to happen? Which of the following statements is true? Well, what actually happens? It's going from a higher energy level to a lower energy level, right? So it has to give up energy. It has to emit light. So which one of these energy is emitted? Okay, Roman numeral 1's good. Roman numeral 2, energy is absorbed. Can't have both at the same time. Right, so 2's out. 3, electron loses energy. Yeah, it goes from higher energy to lower energy. Right, electron's losing energy. The electron gains energy. Nope. The electron cannot make this transition. I beg to disagree. They do that day in and day out. Billions and billions of times a second. So it's 1 and 3, which is B. Let's see, 21 and 22. You know, I think we got similar questions to those weird ones that we don't like in the other class, only they're disguised in this one. 21. Let's see. Emission spectrum of hydrogen contains a continuum of colors. Well, that's false. Right? That's the incorrect one. I mean, if test-taking technique, if you look at all the other selections and you know A is wrong, and none of the other selections say 2 of the above, none of the above, 3 of those weird ones, then we found our answer. And we can stop there. The answer is A. How about 22? Which of the following statements best describes the Heisenberg uncertainty principle? All right, what's the Heisenberg uncertainty principle? Uncertainty. What does this say? It has something to say about position, right? This refers to like the uncertainty of the position. Like we've got a change in position that we can't quantify. And then the other one is change in momentum, or mass times velocity. Okay? And that has to be, let's see, is it greater than or less than? I think it's greater than. Greater than or equal to Planck's constant over something. There you go. So that's the mathematical expression for Heisenberg's uncertainty principle. What does it mean in words? It means that especially for small particles, subatomic particles, you cannot know both where it is and how fast it's moving, or its energy. The mass is going to be the same, right? If it's an electron, the mass is not going to change. So if you know exactly where it is, you got no idea how much energy it carries or how fast it's moving. And if you can define the energy, then you can't tell where it is either. That's the way we go in describing electrons around atoms. We go for the energy. We define the energy, and then we say, use probability for the rest. It could be in this region. That's known as an electron orbital. So we use probability for this, and we get this one pretty close. Now, which one of these statements is closest to that? The exact position of an electron is always uncertain? No. It's just we choose the uncertainty of the position in favor of the other one. So A is false. The velocity of a particle can only be estimated. No, you can nail it down, you just don't know where it is. That seems strange, doesn't it? Usually we think if I know how fast that car's moving, I know where it is here, I know where it is there. But the way subatomic particles work, the velocity and the position can't be known at the same time. So it's not B. C, it is impossible to accurately know both the exact location and the momentum of a particle. That's true. That's the Heisenberg uncertainty principle. They said it better than I did. Okay. All right. Now, in 203, we've already done this, haven't we? Electronic structure. Yeah. Okay, so you shouldn't have any trouble with this one. Just more practice. Okay, let's take a look at 25. How many f orbitals have the value of n equals 3? So we're looking for number of f orbitals when n equals 3. Okay? So what's the next one? L. How many L's are there? 0, 1, and 2. N minus 1 is the highest you can get at an L. Okay? Well, as it turns out, that's as far as we need to go. Because this is S, right? This is P, and this is D. There are no f orbitals with n equals 3. There would have to be 3 here to be an f. So the answer is 0. Right? There are no f orbitals. This is a trick question. How about 26? I got that one highlighted. Yeah. How many f orbitals have n equals 6? Okay, now we're talking. N equals 6. L equals what? 0, 1, 2, 3, 4, and 5. So how many f orbitals have n equals 6? F orbitals. Here's F. All right. So remember our convention. This is a shell. This is a subshell. And M sub L is an orbital. Okay? By convention, that's the way we name them. So how many orbitals are at this level? Well, if we take this one and expand it, how do you expand L into M sub L? You go from minus L to plus L by whole number increments. So minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. 1, 2, 3, 4, 5, 6, 7. 7 equals B. Okay? And by the way, each one of these orbitals can have 2 electrons each. Right? Plus 1/2 spin, negative 1/2 spin. So how many electrons can you have? 7 times 2 is 14. And where on the periodic chart are the f orbitals being filled as we create the next largest, atom or element in the sequence? The actinides and the lanthanides. Those that on the bottom. And if you count them across, there are 14 of them in each row. That's because 14 electrons, which means 14 protons. Okay? All right, 27. If n equals 2, how many orbitals are possible? 27. If n equals 2, shell, subshell, oops, can't do that. There we go. M sub L. How many of these M sub L's can we have? Well, minus 0, 0, and plus 0, right? It's only one. You can only have one of these, right? And then how many of these can you have? Minus 1, 0, plus 1. So 1, 2, 3, 4. You can have 4 orbitals with n equals 2. How many electrons is that? 2, 4, 6, 8. 8 electrons. That's where we get the octet. If you go period 2, period 3, you go 2 electrons here for the alkaline metals and alkaline earths, and you go over here for a boron group, carbon group is this one, and then nitrogen group, oxygen group. Well, actually, they're all together. But there are 8 electrons across that row, 2 in the S and 6 in the P's to get to neon or argon. Yeah, 28. 28. A given set of p orbitals consists of how many orbitals? Well, I kind of just told you. So p orbitals are L equals 1. So m sub L is the number of orbitals. You can have minus 1, 0, plus 1. Right? L equals 0 is S. L equals 1 is P. So you can have 3 orbitals at the P level. 29. Which of the following is an incorrect designation for an atomic orbital? Okay. A, B, C, D, and E. 1s, is that correct? Yeah. Hydrogen and helium swear by it. How about 3D? Is that possible? You can go through the, do the N and the L and the M sub L's to be sure. But, well, you don't need M sub L's, just N and L. But if you look at the periodic table, right, you got the third period. If you go third, you go 3s, 3p, and you skip the d's. When do you get the d's? When you come down to the fourth. Right? You go 4s, then 3ds. And all of those first transition metals are 3d orbital filling. So that one's true. Right? These two are both true. How about C? 1p. That ought to make your ears hurt. No such thing as 1p. You got to have 2 before you can get a p. In fact, 1s is as far as you can go. That's why helium's up there on the left by itself, on the right by itself, and hydrogen's up there by itself and helium. Because there's just a 1s, 2 electrons each. That's as far as you can go. You got to come down to 2 before you can get p. 2s and 2p. Okay? So this one is wrong. And we could talk about the others, but they're all right. The one that's wrong is C. Let's see, we can get 31, 32, and 33 in there. Let's see. I hesitate to look at my watch. Almost used up an hour. 31. So if I mark some that we're starting to repeat ourselves, then I'll skip them. This is new. A point in the wave function where the amplitude is 0. Remember the wave function of Schrodinger? We didn't talk about Schrodinger in the other class. Where the probability of finding an electron the point in that wave function is called a node. Right? We drew graphs. We had graphs like this. We went up like, excuse me, not that. Didn't do that. We did like this. Something like that. This is a node. There's no probability of finding an electron at that position. Okay? This would be energy. This would be position. They're called nodes. (32) How many electrons in an atom can have the quantum numbers n equals 3, L equals 2? Okay. I guess I better do these two also. N equals what? 3 and L equals 2. N equals 3, L equals 2. How many electrons can you have? Okay. So, we've selected 2 out of that one, right? So we don't have to deal with this one, but we do have to expand it further. Right? 2 means minus 2, minus 1, 0, plus 1, plus 2. And then M sub S says each one of those can have a plus 1/2 or a minus 1/2. So you can have 2 in each one. 2, 4, 6, 8, 10. You have 10 electrons with that designation. C is the answer. (33) How many electrons can be described by the quantum numbers n equals 3, L equals 3, and M sub L equals 1? Is that even possible? I mean, we took the one answer 32, we took that as true. But maybe we need to take another look at this one. Can L equal 3? No, it has to be 1, 0, 1, or 2. Right? It can't be. Another trick question. It's 0. You can have no electrons with those numbers. (34) What's the L quantum number for a 4s orbital? 34. Let's work it out. It says 4s. 4s. Well, n equals 4, right? And L equals 0. Right? So, oh, okay, yeah. 0. Oh, I was overthinking that one, right? Because L 0, 1, 2, 3. This would be S, P, D, F. So all we had to look at was the S and say 0. (37). Let's see if that's worth stopping at. What's the following which of the following combinations of quantum numbers do not represent permissible solutions of the Schrodinger equation? All right. So we've got N, L, M sub L, and M sub S. And the first one is 9, 8 minus 4 and a half. 9, 8 minus 4 and plus 1/2. Okay, the second one, let's see, this is A, B, C, D, and E. All are allowed. So all we have to do is find one that's not allowed, and E's out. 8, 2, 2 and a half. 8, 2, 2 and a half. C, 6 minus 5 minus 1 and a half. 6 minus 5 minus 1 and a half. And 6, 5 minus 5. 6, 5 minus 5 and a half. Okay. So, is this one allowed from that? Well, yeah. This is n minus 1, so that's okay. But then we take this one and say minus a, minus 7, minus 6, all the way up, minus 4. Yeah, that's allowed. And plus 1/2 is allowed. So A is okay. How about this one? 8. Can we do a 2L out of that? Yeah. 0, 1, 2, 3, 4, 5, 6, 7. So that's okay. How about, can we get a 2 out of this one? M sub L. Well, this one will be minus 2, minus 1, 0, plus 1, plus 2. Yep, we can do that one. And that one's allowed. How about this one? If we got a 6 here, can we get a minus 5 out of that? No, you can't get any minuses, L's, out of the N's, because they're 0, 1, 2, up to N minus 1. So that's the sticking point right there. Won't work. And it doesn't say 2 of the above, does it? Okay, so we found our answer right there. That's the bad one. $37.40. This is a memory problem. Who was the first chemist to recognize patterns? Patterns in chemical properties of the elements. The temptation is to go straight to Mendeleev. That's why he's first. But that would be wrong. Who preceded Mendeleev with this recognition of similar chemical properties? Do you remember? It was Dobereiner. Dobereiner and his triads in 3 elements that have similar properties, like the halogens. That's one. He had several others, but that's our example. So Dobereiner is the answer. Bohr had nothing to do with it. Lothar Meyer was a contemporary of Mendeleev. So he and Mendeleev put together their whole periodic tables. I think we've got a question about Mendeleev in a minute. Let's see. Yeah, it's the next one, as a matter of fact. So focusing on Mendeleev, he is given credit, the most credit, for the concept of the periodic table of the elements because what? What was so special about Mendeleev? He used the periodic table, his created table, and remember when he started putting elements in his table, he would come to a group and the next element didn't fit the group. It moved over one more to a different group. And he had a blank space there. So instead of just leaving it, he said, one of these days, somebody's going to discover an element right there, and it's going to have these properties. And they put it in there and complete my table. Sure enough, they did. So his use of the periodic table as he created it to predict the existence of as yet undiscovered elements was the reason he got more credit than anybody else. So that would be B. He emphasized the usefulness in predicting the existence and properties of unknown elements. Let me see, 44. Yeah, I guess we better do this one. The complete electron configuration of 10. 44. So how do we do this one? What's the symbol for 10 anyway? You don't remember? It's one of those Latin ones.
I like MCM.
Yeah, that's it. Stannum. Okay, so what do we need in order to write the electronic configuration? Well, first you need the number of electrons. So we look at our periodic table and we find that 10 has 50. The neutral atom has 50 protons and 50 electrons. And then we write out in shorthand our series of orbitals, and then we start filling them in with electrons. So it goes like this: 1s, 2s, 2p, 3s, 3p, and then it goes 4s before it goes to 3d. Okay, we might need more, but we won't worry about it right now. Okay, how many electrons can go in an s orbital? Just 2. So we put 2 in that one, 2 in that one. How many can go in the p orbital? No idea? Remember, it has 3 levels: -1, 0, +1. Yeah. Okay, so it has 6. Then we have 2 more here, 6 there. Let's see how many we got so far. This is 10. This is 8. We put 2 more here, and this becomes another 10. Right? Is that right? 10? Yeah. Okay, so we are going to need some more. So what comes after 3D? 4p. Right? So we got 20 used up. We need 30 more. So this, how many in D's? How many elements across the period in the D section of the periodic table? Transition elements. 10. These have 10. All right. 20. Another P has 6. So that's 14. Now where do we go? Well, let's see. 4 P's gets us to krypton. Now we're going to 5s. That's 2. And what's after 5s? Back into the D's. Remember, we back down 1. 4D. 10. Well, yeah, that's full. Now, once we get past the 4Ds, we go back to the 5Ps, right? So how many have we used up so far? I lost count. 6, 2, 12. We need 2 more. There we go. So that's the electronic configuration for 10. And we just look at our selections, and we go down and look for 5p2. So let's see, how many have 5p2? A, C, and D. Okay, so we can throw out B and we can throw out E. Let's see, what's next over? 4D10. 4D10 is D. That's it. We found it. That's the beauty of multiple choice. Okay, how would we write this in abbreviated shorthand? Put this back here. Remember that one? You find 10. All right, there's 10. See, 50. You back up to rubidium, and then you go up the next one, and we find krypton at 36. That's the core. So from krypton, we go through 5s here, like that. 5s2, 4d10, and 5p2. That's the abbreviated shorthand for 10. Okay? All right, let's scroll down some more. See, do we need to stop here? Yeah, this is definition. (46). The statement that the lowest energy of configuration for an atom is the one having the maximum number of unpaired electrons allowed by the Pauli principle in a particular set of degenerate orbitals is known as, we haven't described degenerate orbitals. Degenerate doesn't mean perverted. In chemistry, degenerate means the orbitals have the same energy level. So if they're at the same energy level, like a p orbital, right, it'll have, well, p subshell, and the orbitals underneath are at the same energy. So what principle says you put electrons in there with maximum unpairing first? You go like this, like this, like this, and then if you have another one, it can go in paired. Right? Well, the answer's up there. It's Hund's rule. Hund says that's the way it goes. And actually, this explains the behavior of atoms. We haven't got there yet. That's next semester, I think. Or is it? General concepts. Maybe not. We might get to that this semester. There's physical evidence that supports Hund's rule. And that's all I'm going to say about it right now. 47. The element has an electron configuration of, oh, that's 10. We just did 10. But if this question comes in complete without that other information, how are you going to tell where it's located? You need to know the structure of the periodic table. Right? If you look at 5p, where is 5p? Go down to the 5th period, right? Starting with rubidium, strontium, yttrium, zirconium, niobium, on across. Then when you get to indium, that's 5p1. And then next one is 10, 5p2. So what is 10? Where is it located? It's a metal, right? See, it's a metal. If we did one that had 4p2, that would be the one above it, right? Germanium. Now, germanium is kind of, it's crossover. It's in that group that we call metalloids. So, yes, it is a metal, but sometimes it acts like a nonmetal. So that's why we call it a metalloid. Arsenic's the same way. Silicon is a metalloid. Let's see, what's another one? Antimony, Sb, and tellurium. Those are metalloids. Now, tellurium is a nonmetal, except when it's not. Right? Under the certain circumstances, it acts like a metal. Okay, 48. I didn't write the number on that one, 47. 48. An element with electron configuration, let's see, yeah, I can get all those three. 48. Has xenon, yeah, xenon, 6s, 4f, 5d7. 6s, 4f, 5d7. Would belong to which class on the periodic table? That question is really simple. The last orbitals that are being filled are d orbitals. And where do we fill those? Transition metals. So you don't even have to find that one in the table. You just know that that says it's transition metal. As a matter of fact, 5d7, 5, 1, 2, 3, 4, 5, 6, 7. That's rhenium, Rh. And it's a transition metal. 49. An alkaline earth, all alkaline earths have the following number of valence electrons. Remember the definition of a valence electron? Those are the electrons that are available for bonding. And they're in the outermost orbitals, and they're all the same principal quantum number. So in all of the alkaline earths, the second column, have how many valence electrons? Well, it's s orbitals, so they can only have two. Two electrons, that's D. Uh, 50. Titanium. Titanium has blank in its d orbitals. So titanium, all you need to do is find titanium. You know where it is. You know where it is? It's in the first row of the transition elements, right? Start potassium, calcium, scandium, titanium. So how many electrons does it have in its valence? How many valence electrons does it have? D orbitals, right? You're filling d orbitals there. Well, that could be a trick question. Which orbital is being filled? 3D. Right? It's in the fourth period, and remember the D's back up one of the ends. So we know it has two, but does it have any more d orbitals that could be filled? No. 3 is the first time you encounter d orbitals. So that's it. That's all. 2 electrons in its d orbitals. The answer is B. Now, if I were tricky, I'd say, okay, zirconium, right? The one right below titanium. How many electrons are in its d orbitals? Well, it's already gone through the 3Ds, so it's got 10 there. Now it's down to 4D, 2. So that would be 12 electrons in its d orbitals. Okay? Just a word of caution, in case I do something sneaky like that. Okay, let's see. Do we need to stop here? Yeah, I guess so. Iron, 52. Iron. What is it asking about iron? Iron has how many electrons are unpaired in its d orbitals? Okay, look where iron is. You're filling the 3Ds, right? Okay. Count over. Scandium, titanium, vanadium, chromium, manganese, 6. 6 electrons in iron's d orbitals. Okay? Wait a minute. Hold on a second. Oh, unpaired. I had to read the question. Okay, it does have 6 electrons in its d orbitals. How many d orbitals are there? 1, 2, 3, 4, 5. Okay? So, how do we fill it up by Hund's rule? 1, 2, 3, 4, 5, 6. Now we can answer the question. 1, 2, 3, 4 unpaired electrons. I outsmarted myself with that one. Does that everybody see where I was headed there? I was down the wrong hole. Chasing Alice. Wonderland. Okay, let's see, we need to have a look at this one. In that grid, where it shows A, B, C, and D, which represents the ground state of nitrogen? Nitrogen. What do we got, 7? Yeah. 7 electrons. So we have 1s2, 2s2, 2p, what? 4. We need 3 more, don't we? 4 plus 3 is 7. Okay. So how are they laid out, though? Because it shows orbitals underneath. Well, these only have 1 each. So they're both going to be like that. This one has 3. 1, 2, Excuse me. So we have paired, paired, 3 unpaired. Paired. Oh, it doesn't show the 1s. It only shows these. Okay, that's fine. So this is paired. This is paired. 2s, and then 3 unpaired. A matches that one. Okay? And 54, we're going to make an ion out of it. Right? If we make an ion, one negative ion, why is it one negative ion? Because we added an extra electron. So where does that electron go? Right there. So now we need 2s paired and 2p, the first one paired, which looks like E. Okay? Okay. Just pausing for recognition questions. Okay. Okay, now we're going to talk about, valence electrons, 55. So what is it about valence electrons that ties elements together? Elements in the same group, at least for the representative elements, the S's and the P's, in the same group will have the same number of valence electrons. So, to answer this question, you just look at your groups. Phosphorus, sulfur, chlorine. Now, they're in the same period, they're not in the same group, so it can't be A. Silver, cadmium, argon. Well, argon, you have to have noble gases paired with argon, and those other two are not noble gases. So B's out. Sodium, calcium, and barium. Well, sodium's in the first group, and calcium and barium are in the second group, right? So they can't have the same number of valence electrons. How about phosphorus, arsenic, and selenium? Phosphorus and arsenic are in the same group, but selenium's in the next one over. Okay? So they don't have the same number of valence electrons. That's what gives them similar chemical properties, is the same number of valence electrons actually coming from the same types of orbits, from the S's and the P's. Right? So none of them are correct. But none of those have the same number of valence electrons. All 3 of them, that is. A couple of them have 2 that are the same, but then the third one's not. So E is the answer for 55. Okay. I'm going to try to finish. I might have to leave 58. All right, 59. Of the following elements, which needs 3 electrons to complete its valence shell? What I would do is I would look at the periodic table and say, completed valence shell would have to give you a noble gas. So if you need 3 electrons, you just back up to the left 3. Right? So it'd be, let's see, fluorine, oxygen, nitrogen group. So it'd be nitrogen, phosphorus, arsenic, antimony. Which one? Phosphorus, D. D needs 3 electrons. Okay? Did I lose anybody? No? Circular nod. Yep. That's why at the very beginning of the semester, when we started learning naming conventions, and we said, all right, what's the possible charges on these atoms if they're going into ionic compounds? Nitrogen, phosphorus, arsenic, those are all in ionic compounds, those are all -3 against whatever cation you throw at them. And that's the reason that they're -3, because they need 3 electrons to complete their valence shell. And they're going to get it from somebody. Let's see. I'm going to skip that one. If I skip any of these that you know, stop me if you think you need them. I'm going to skip 62. So you may mark that down, take a look at it later. The description, the answers are going to be in that review document. The worked problems, I hope. Let's see. Let's do 67. Ionization energy of bromine. How would we write that? What reaction is occurring that requires ionization energy for bromine? Remember, we have to start with a gas. Remember why? You won't remember why because we didn't cover it. Because bromine at standard temperature and pressure is a liquid. And you got to add energy to it to make it a gas. Right? You don't want to call that energy ionization energy because there's no ions moving. You just broke bromine apart from a liquid and you made bromine liquid, separate atoms. That took energy. And then you take this one and you make a gas. That takes more energy, right? So ionization energy equations always start with a gas of the single element. Doesn't matter if it was diatomic at room temperature and pressure. It's that way. So ionization energy means now we're going to liberate an electron. Okay? So we add energy into it, knocks the electron off. And that amount of energy is the ionization energy. In this case, the first ionization energy. So we kicked off only one electron. But you could do it again. You can take this one, find out how much energy it takes to kick that one off, and then the third one, whatever. Okay. Increasing ionization energy in the periodic table. What's the trend? 68. So here's your periodic table. Increasing ionization energy. Lower left to upper right. So which group of these three elements says for sulfur, chlorine, and fluorine that they're in the proper order of increasing ionization energy? Well, let's see. Sulfur, and then, what's the other one? Chlorine, fluorine. Where's chlorine? Chlorine's over here. And then fluorine. So increasing would be sulfur, chlorine, fluorine. A. How about increasing atomic radius? What's the trend for atomic radius? That's just the opposite, right? Right to left, top to bottom, increasing. So what would that be? Well, just flip it around, right? It would be increasing atomic radius, correct? Yep. Be fluorine, chlorine, sulfur. D. All right, I'm not going to do 73. You can do that one. And I'm not going to do this one either. All right, 77 is repetitive. We've been through that one. 78 also. 9. All right, this 80 is just testing your memory. 80. So N, L, M sub L, and M sub S. And the principal quantum number says things about energy and size of the orbitals. L, which is the magnetic quantum number, I think. No, this one is the angular momentum. Angular momentum. What is it talking about? It's talking about shape. What's the shape of the orbital? So SPDF, S is spherical or shell with its nodes. P is kind of dumbbell shaped, remember? There's X, Y, and Z, so we'll have one like this, one like that, one like this. Okay. That's shape. Well, the orientation on these directions is the magnetic quantum number. That's the one we're after. This is orientation. Okay, orientation in space. And remember, when we draw these representations of orbitals, these are just probabilities. These are the places that you're most likely to find the electrons. And we're saying that wherever you don't find that shape is a node. They don't exist there. All right, so D is the answer, shape. There's copper. Oh, copper. Maybe we better do this one for copper. We didn't talk about anomalies on electron configurations, but copper's a good example. '84. Copper. All right, copper has 29 electrons. Okay. And 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. Now we get over to copper. Count from the left. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper. 9 electrons. That's what you would expect. But that's not the configuration for copper. And here's why. The electrons find themselves in places with the lowest possible energy. Well, once you get up to 9 Ds, how many maximum you can have in D is 10, right? Well, as it turns out, if you're that close to being a complete D, it may be to an advantage to steal an electron from somebody else and put it in that D orbital and make 10. And that's what copper does. Copper does this. It says, right, it's got 1, 2, 3, 4, 5. So what it does is it takes one of these 4 S's and completes its D's. That's one of the anomalies in the electronic configurations. Copper's like that. Silver's like that. It happens in the middle of the table too. 1, 2, 3, 4, 5. Let me see. Yeah. Chromium. Chromium does it. But chromium does it with half-fill D. It steals one of these and just puts 5 in here. Right, so apparently there's some stability that's advantage to half filling the Ds and completing the Ds, that it would go ahead and steal an electron from the 4s. Okay, so that means that the configuration is B in that abbreviated shorthand. Notice we go back to argon, then we work our way from argon down to potassium, which is 4s, then calcium is 4s1, 4s2, and then we work across 3 Ds. Okay. All right. Oh, 85. Electron affinity for X. X could be any element. That one's pooping out on me. '85. How do we write electron affinity? Well, you don't start with the negative ion or the positive ion and then add the electron back to it. You always start with a neutral atom, and it has to be in the gas state. So whatever the element is, it's got to be in the gas state and neutral. We want to know, how does the neutral atom attract an extra electron? So we add an electron to it, and that gives us X minus gas. That's the formula for electron affinity, first electron affinity. So what kind of energy do you get out of that? Well, when an electron falls from infinity down to an orbital, it has to give off energy. It's going to a lower energy state. And by our convention, if this is the system, then the value of the negative energy, of the energy that's leaving the system, has to be negative. Right? So the bigger negative energy you have, the stronger the affinity of the electron for the atom. And you find that those are more negative toward the upper right part of the periodic table and less negative down at the lower part. Okay? It's the same trend, but different numbering system. Right? Because ionization energy, you have to add energy to get the electron off. So it's more positive, lower left, upper right. But electron affinity is lower left, upper right, more negative, which means a stronger affinity. 85. Let's see, which of the following decreasing, we did one of those. All right. Let me hold this one in reserve. Come back to it. 87, because that's going to take a little time to do. There's another one in here like that also. All right, let's do 89. 89 should be fairly simple. In the hydrogen spectrum, what is the wavelength of light associated with n equals 3 to n equals 1? So we're going from n equals 3 to n equals 1. So, what's the energy transition there? Well, how much energy? Is it going to be giving up or absorbing energy? If it goes from N3 to N1, it's going from higher energy to lower, so it's going to give off energy, right? It's going to emit light of a given wavelength. So what we need is, what's N equals 1 is minus 2.178. Minus 2.178 times 10 to the minus 18 joules. That's N equals 1. N equals 3, we subtract a minus 0.242. 0.242 times 10 to the minus 18th again? Yeah. Okay, so this is going to be a positive because we're subtracting the initial from the final, and that means it's going to have the same power. I did the same power here. So we just say, all right, this is going to be, let's line these up, 178. Yeah, I got an extra 0 out here. 6, 3, 9, 1.9, negative 1.9. Now that's the actual energy transition. But if we're going to do a calculation with it, we don't need the negative. We just need the change in energy. And the change in energy will give us the frequency or the wavelength, depending on which formula we use, right? So this energy is equal to what? Planck's constant times frequency, or Planck's constant times speed of light over wavelength. Okay? Now if we do that calculation, Planck's constant is that weird number, 6.626, I think, times 10 to the minus 34. And then this is 2.9979 times 10 to the 8th meters per second. And there's the other value for energy we just saw for our unknown. Okay? And we should come out with 1.03 times 10 to the minus 7th meters as the wavelength of light. Uh, 90 is repetition. Which of the following is a reasonable criticism of the Bohr model of the atom? 91. Well, let's see. It makes no attempt to explain why the negative electron does not eventually fall into the positive nucleus. It just ignores it. It doesn't say anything about it. It does not adequately predict the line spectrum of hydrogen. Oh, it does that. It does not adequately predict the ionization energy of valence electrons for elements other than hydrogen. It does not, no. It does not predict accurately for any other element except hydrogen. That's it. That's why C is the best answer. Let's see. I'm going to skip that one. This representation of the 2p orbital, which of the following statements best describes the movement of an electron in a p orbital? First of all, we don't know much about a movement. Right? We're focused on energy. So in order to know movement, we need to know position. Actually, the best description is E. We cannot be exactly determined. The electron movement can't be determined. No matter what orbital it is. It doesn't have to be a p orbital, any orbital. We don't know anything about its movement. In fact, the best representation of electrons now in an atom are waves. So I've seen it drawn this way. If you have an orbital around an atom, around a nucleus, like that, they represent the electron as like this. It's just a wave. And I think that was the basis for Schrodinger's equations, because in order for this wave to fit at a certain distance from the atom, it has to be a perfect fit. In other words, you can't end up here away from where you started. It's not harmonious. It's got to go here and then continue. Okay. I'm going to skip that one. Let's see. All right, 96. The small but important energy differences between 3s, 3p, and 3d orbitals are due mainly to what? They have different shapes. They have different orientations in space. but they're all principal number 3, which means their energies should be similar, but we know they're not exactly the same. So what explains that? The best explanation is that penetration effect, right? And we didn't cover that in 203. The penetration effect is when you see a representation of the orbitals, say like that, you got these nodes here, but maybe another, this might be an S orbital. Well, a P might have a major hump right here. Right? The major hump is closer to the nucleus than the S is. Right? But the S has penetrated with its, between the nodes, it's penetrated closer to the nucleus with a substantial amount of its probability. So that gives it a lower energy than the P. And you can make a similar argument for the Ds. So the difference between their very small differences between their energy levels is due to that penetration effect. D. D's the correct answer for that one. All right. We looked at nitrogen earlier, and it in this 2p orbital, it has 3 unpaired electrons. You remember that description, so I don't have to stop there. How about 101? An element E has the electron configuration krypton 5s2, 4d10, 5p2. The formula for fluoride, the fluoride of E is most likely what? Well, we look at the valence electrons. I think that was 2 and 2 on either side. Yep. So what are the possible ions that could form here? Well, the valence electrons have the same principal quantum number, and they're the highest principal quantum number. So these 2 and these 2 are the valence electrons. If we got rid of all 4 of them, ionized the element for that, then we would have what? 4 plus, wouldn't we? You get rid of 4 electrons, you have 4 protons left over, 4 plus. But another possibility is, since these are higher energy than those, maybe we only lose those 2. 2 plus is another possibility. What's fluorine? Fluorine's always -1. Okay? So if it's 4 plus, that means we need 4 fluorines. And if it's 2 plus, we need 2 fluorines. So it's either XF4 or XF2. Oh, I'm sorry, it was E. Okay, let's be consistent. There we go. EF4 or EF2. So let's see our choices. There's an EF4, but there's no EF2. So our best answer is B, EF4. Okay? That's emphasizing the significance of valence electrons in their chemical reactivity. Well, maybe we better stop at 104 also. Second ionization energy. All right, which following atoms have the largest second ionization energy? So we got magnesium, chlorine, sulfur. Magnesium, chlorine, sulfur, calcium and sodium. Calcium and sodium. All right. So what does magnesium have? It has 2s. Yeah. 2s2. Chlorine has 3p. It has 3s2, 3p5. And sulfur has one back from that. 3s2, 3p4. Calcium has 4s2. I'm just doing the valence electrons. That's all we need to know right now. Sodium is 3s1. Okay? Now, what happens? What would be the second ionization energy for this one? Which electron would be removed? Well, it'd be another s electron, right? We remove one, and then we still got another s. So we're still moving valence electrons. Here, we're still removing valence electrons. Here, still valence electrons. Here, still valence electrons, right? 4s2, 4s1, we take that one off. That'd be the second ionization energy. Here, we got 3s1 for sodium, and then we have 2p. 2p6. If we take this one off, now we're trying to remove a core electron. And the core electrons are very stubborn. They take a lot of energy. So this one, the second ionization energy, would be highest for sodium. Those chairs getting uncomfortable? Should be. Let's see. I'm not going to do that one. We talked about that already. 108 is a good one to do if I got time. 87 and 108 are going to take a little time to do those. So let me be sure I don't miss anything else. Okay. I think that's unduplicated. So let's go back to 87. What, I got 10 minutes? Well, actually, they cut us off earlier than that, don't they? No, 3 o'clock. Yeah, maybe I can get one of them done. Ah, 87. Here we go. 87. I need a better marker than that one. See if I got a. Here's a blue. Maybe this will work. Okay, we have an atom traveling at 1% of the speed of light. So we have one atom. Velocity equals 0.01 times the speed of light. 1%. Right? So that means it's 2.9979 times 10 to the 6th meters per second. That's its velocity. Right? This is 10 to the minus 2, and 8 means 10 to the 6th. All right, what else are we given? The de Broglie wavelength is found to be 1.46 times 10 to the minus 3rd picometers. 1.46 times 10 to the minus 3 picometers. And this is the de Broglie wavelength for that atom. We mentioned de Broglie earlier. Which element is this? What do we need to find out what the element is? We have two choices, right? We could do, if we could find the Z number, right, the number of protons, we could do it easy. But I don't see how we're going to get the number of protons out of that. What we might be able to do is get the molar mass, right? How much does 1 mole of that atom weigh? And that's kind of like this one. Not exactly, but close. And then you could go to the periodic table and get pretty close to it. Okay? So, how do we get the mass out of this? That equation, right? This relates velocity and mass if we know the energy. How do we get the energy? From the wavelength. Okay? So we've got these two equations, right? But that wavelength, we need to do this, this, and that. Okay? Now, the next thing I'm going to do is kind of a little algebraic magic. Combine these two equations. Because what we really want to know is what's the mass of that atom. If we can find the mass of one atom, then we can expand it to a mole and do its molar mass. So, what do these two have in common? Well, they're both equal to energy, right? So, we have that going for us. mc squared equals hc over lambda. So if we solve this equation for mass, then we can say hc over lambda c squared. And then cancel one of those and one of those. Okay, now we have Planck's constant over lambda c. All right, problem is this atom's not moving at the speed of light. Right? It's moving at its own speed, 1% of the speed of light. So de Broglie says you can substitute here the actual velocity right there. So the equation now becomes h over lambda times v. What's the speed of that atom? Okay, so let's see. We got wavelength. Wavelength needs to be in meters. So here we have this prefix. What's a pico? 10 to the minus 12. So that means minus 12 and minus 3 is minus 15, right? 1.46 times 10 to the minus 15 meters. Now we got this one, we got this one, and we just need Planck's constant, which I don't have memorized. Yeah, 6.626, 10 to the minus 34. Okay. 6.626 times 10 to the minus 34 joule seconds. Wavelength, 1.46 times 10 to the minus 15 meters. And velocity, 2.9979 times 10 to the 6th meters per second. Okay. Is that going to work? Did I put the right units for? Yeah, joule seconds. Okay. Yeah, that's right. And our answer is going to come out with what? It's going to come out in SI units, which is kilograms, right? Kilograms. Okay, so we just need to do that calculation and find out what the mass of that one atom is. All right, 6.626 to minus 34 and 1.46 exponent negative 15 divided into that, and then 2.9979 exponent 6 divided into that. And I get the mass equals 1.514 times 10 to the minus 25th kilograms per atom. Okay? Now we've got the ratio, mass per something, mass per atom. We can convert that to mass per mole. Now it just becomes a dimensional analysis problem. All right? Let's do atoms first. Atoms on the bottom over there, so it's top here, moles on the bottom. So it's 6.22 times 10 to the 23rd atoms per mole. Right? That gets rid of atoms, got moles. Now we need kilograms. Right? kilograms on the top there, so it's on the bottom here, grams there, 10 to the third grams per kilogram. So all we have to do is take that value, multiply it by Avogadro's number, and again times 1,000. And I get 94.2 grams per mole. Now let's see, let's look at the periodic table. I'm going to get close enough to see it. It looks like, ooh. Is that right? 94.2. Did I make a, I think I made a calculation error. This says the answer is zirconium. Let's try it again. I have to go back down to this one. 6.626 exponent 1.46. Did I write them up there wrong? 10 to the minus 3. No, that's right. Exponent minus 15 divided 2.9979 exponent 6 divided. No, that's right. Oh, that's wrong, isn't it? 6.022. Avogadro's number. That's where I boo-booed. .2 grams per mole. And that puts us at zirconium. Okay? Think you could do that one from scratch if we gave you a different set of data? Might be a stretch. Be a good bonus question. 108 would be a good bonus question too. I ran out of time. I wonder, we got to do calorimetry. It's going to take us, well, if we work as a single group, it may not take us a whole 2 hours. So let me finish this one. 108. Okay. Let's see. Close, close, close. There it is. Okay. 108. Consider a planet where the temperature is so high that the ground state of an electron in a hydrogen atom is N equals 4. That'd have to be pretty hot. What's the ratio of ionization energy for hydrogen on this planet compared to that on Earth? Okay. So we've got an exoplanet with an ionization energy. And let's see, the ratio is between one for the planet over the one for the Earth. So the ionization energy for the exoplanet has a ratio of that for Earth. That's what we're looking for. So how do we tell the energy of transition energy for the electron to go from ionization on this one to ionization on that one? In this one, we've got to go from N4 to N infinity. Right? Infinity means it's left the atom. And this one, we've got to go from N1 to N infinity. Okay? So how do we calculate that one? Well, let's see, there's an equation for that. And it's in useful information, and it's right there, kind of 2/3 of the way down in the middle in a big block. Minus 2.178 times 10 to the minus 18. So we go from final minus initial. So this one is going to be minus 2.178, is it? You guys ought to read this off for me. 178, 10 to the minus 18. 10 to the minus 18 times what? The number of protons squared over the energy level, the quantum number squared. Okay? So this one's going to be the final, right? And n for this one is infinity. Square infinity. Have you ever done that before? Neither have I. I don't think it can be done. And what's the Z number? This is a hydrogen atom, right? It's 1. So that's the infinity. Now n equals 4. And we subtract a minus, let's see, let's make it square brackets, minus 2.178 times 10 to the minus 18 times 1 squared, it's still a hydrogen atom, and now we're at level 4, right, squared. Okay? We're going to ratio that to what it is on Earth. The same thing, right? It's going to infinity. Subtracted is minus 2.178 times 10 to the minus 18. Now on Earth, it's this one squared, but that one squared. Okay? That's the ratio. This is the energy of transition for the exoplanet. This is the energy of transition for the Earth. We just need to ratio them. Right? So, what do we got in common here? We got this factor is the same for both of them. And the same for this one. So in algebra, we can do what they call factor those out. So we can say this one comes outside, and now it's this term minus that term. But what is this term? Anything divided by infinity is 0. Right? So these two terms completely drop out. And this negative times that negative is a positive. Right? So now what we have is this divided by that. This is a common term on numerator denominator. Now we have to work with is this to give us our ratio. Right? So what is this one? This is 1 over 16, and this is 1 over 1. Right? So 1/16 divided by 1 is what? 1/16. So the ratio is 1 to 16. That's why the answer is C. Okay? Now, if you go into the worked problems and look at this one, you will see that I actually calculated the energies. That was several years ago before I got smart and decided to do some real math before I get to this end. And that solves the problem much easier than doing those calculations. There's less chance for error, too. Okay, that's it. Any questions, comments?